Welcome to the deep dive, ready to explore how machine learning is being used to predict rock slope stability.
I'm ready.
Perfect. We're diving into a brand new research review paper from Geotech Geol Eng, Rock Slope Stability Prediction, a review of machine learning techniques, published just last month, February 2025.
Hot off the press.
And I know our listeners are already familiar with the importance of rock slope stability, especially in geotechnical engineering, landslides, failures, the whole shebang.
Yeah, preventing those is kind of our bread and butter.
Exactly. But what's really got everyone buzzing is this shift away from those traditional methods towards machine learning.
It's a pretty exciting time to be in the field, that's for sure.
So let's unpack it all. How are these new techniques working? What makes them so effective? And, what challenges are we still grappling with?
Sounds like a plan.
Great. So before we dive into the world of machine learning, let's take a step back and revisit those traditional methods like the limit equilibrium method or LEM.
Yes, the LEM. That involves analyzing all the forces acting on a potential failure surface, and then we calculate that all-important factor of safety.
So basically, are we going to see a landslide or not?
Exactly. And then we have our computer simulations like the finite element method and the finite difference method, FIMM and FDM.
Right. Those are the ones that create those cool, colorful models showing how the slope behaves under stress.
That's them. Those methods have definitely served us well over the years, but they do tend to struggle when things get a bit more, shall we say, complex.
Complex how?
Well, imagine a slope with tons of different rock types or maybe groundwater conditions that are constantly changing. Those variations can make it incredibly tough to create a reliable model using those traditional approaches.
Got it. So a little too much real-world messiness for those models to handle.
Pretty much. And then you have those empirical systems like the rock mass rating and the geological strength index, the RMR and GSI. Those rely heavily on expert judgment, which, as you can imagine, can sometimes introduce subjectivity.
Ah, the human element. Always a wild card.
Isn't it, though? That subjectivity can make predictions less reliable. Plus, some of those methods, especially FEM and FDM, can be quite computationally intensive. They need some serious processing power, even for, what seem like relatively straightforward scenarios.
Okay, so I'm sensing a theme here. Traditional methods, while valuable, have their limitations, especially when dealing with real-world complexity. Enter machine learning.
Cue the dramatic music.
But before we jump into that, can we go back to those limitations for a second? I'm thinking about the limit equilibrium method. You mentioned heterogeneity being a challenge. Can you give me a real-world example of that?
Oh, absolutely. Let's picture a coastal cliff. The dramatic kind.
Yeah.
And it's got layers of sandstone and shale, all crisscrossed by fractures with groundwater seeping through, trying to pick out that single, reliable failure surface using the LEM. Nearly
Right.
impossible. Too many variations in that rock mass.
Oh, okay, that's a great visual. So basically, the real world throws a wrench in those idealized models.
It does. And that's precisely where machine learning comes in, ready to embrace all that complexity.
It's like those algorithms are saying, bring on the messiness.
Right. Machine learning, or ML, uses algorithms that can chomp through massive amounts of data, all those geological variations included. And get this, it can even factor in real-time data, like seismic activity or rainfall, to create these really dynamic risk assessments.
That's amazing. We're not just looking at a static snapshot anymore. We're getting a real-time view of how those slopes are behaving.
Exactly. It's a game changer.
So what are the ML techniques being used? This paper mentions so many, like CNNs, SVMs, RFS. It's an alphabet soup of acronyms.
Let's decode that soup because each technique brings something unique to the party. First up, we've got convolutional neural networks, or CNNs. Think of them as pattern recognition experts, especially good at analyzing images.
So they're looking at photos and maps of rock slopes, trying to spot those telltale signs of instability.
You got it. The paper even mentions a study where a CNN achieved a 95% accuracy rate in identifying what are called key blocks in a rock slope in Iran.
95%. That's incredible. But I have to admit, I'm not familiar with the term key block. What exactly is that?
Great question. A key block is like, it's a potentially unstable rock mass that, if it were to move, could trigger a much larger landslide. Think of it as the linchpin holding everything together.
Oh, wow. So identifying those key blocks is crucial for preventing those catastrophic events. And a CNN can do that with 95% accuracy. That's a huge step forward.
It really is. especially in complex geological settings where those traditional methods might miss those subtle clues.
So CNNs are our pattern spotting superheroes. What about those support vector machines or SVMs? What's their specialty?
SVMs are the judges, you could say.
Mhm.
They analyze all the data about a slope and then draw this boundary line,
Yeah.
separating the stable slopes from the unstable ones.
Okay, so they're not just saying stable or unstable, they're actually giving us a more nuanced assessment.
Right, and they're particularly good at predicting the factor of safety, or FOS.
Hmm.
That's a key metric for engineers.
Right, that tells us how close a slope is to failure, right?
You got it. And SVMs are consistently ranked as one of the top models for predicting that FOS, with really high accuracy.
So CNNs are our detectives, SVMs are our judges. What about those random forests or RFs? Where do they fit in?
RFs are the team players. They use a whole bunch of decision trees, each one looking at the data from a slightly different angle, and then they combine all those predictions.
So it's like getting a second opinion or even a third or fourth to make sure we're getting a more well-rounded prediction.
Exactly. And because RFs can handle those massive data sets, they're perfect for analyzing real-world slope data, which is often messy and full of variables.
The real world loves to throw us curveballs, doesn't it?
It does. And the paper actually highlights a study where RFs really shined. They outperformed other ML models in predicting mine slope stability using a huge geotechnical database.
So RFs are great at sifting through all that noise and finding those hidden patterns that other models might miss.
Exactly. That makes them super valuable for real-world applications where the data is, well, let's just say, less than ideal.
This is fascinating. We've got our pattern spotting CNNs, our judging SVMs, and our team playing RFs. What other ML techniques are shaking things up in this field?
Oh, there are a couple more we need to talk about. Gradient boosting machines, or GBMs, are like, well, imagine a group of experts learning from each other's mistakes.
So they're constantly refining their predictions, getting better over time. That's both impressive and a little intimidating.
Right. GBMs are really good at figuring out which variables are the most important for predicting slope stability. The paper describes a GBM model that nailed down slope height and cohesion as the big players in predicting those circular failure mechanisms.
So they can tell us not just whether a slope is likely to fail, but why it's likely to fail. That's incredible.
It is. Gives engineers valuable insights into the underlying mechanisms driving those failures.
Okay, I'm loving this. We've got our CNNs, our SVMs, our RFs, our GBMs. And what about those Bayesian networks or BNs? They sound a little mysterious.
The GNs are the ones who can handle uncertainty,
Right.
which in geotechnical engineering, that's kind of a constant companion.
You're telling me we're always dealing with unknowns and what ifs. So how do BNs manage that uncertainty?
Well, they actually bake those probabilities and uncertainties right into their predictions, which makes them super useful for risk assessment. And they can handle data from multiple sources, geological maps, sensor readings, weather forecasts, to give us this more holistic view of the situation.
Okay, so they're like the master integrators bringing all that data together and figuring out how it all fits into the big picture.
You got it. The paper even talks about how BNs were used to predict debris flows in northern Iran, and they achieved a forecasting accuracy of over 90%.
Wow, over 90%. That's incredible. So they're not just good in theory, they're actually delivering those accurate predictions in real world situations.
Exactly. And especially in those situations where we have, incomplete data or things are constantly changing, BNs can really rise to the challenge.
All right, so we've got our pattern detecting CNNs, our judging SVMs, our team playing RFs, our learning GBMs, and our uncertainty handling BNs. Is there anything else I'm missing from this ML toolbox?
We can't forget about those hybrid models. They combine the best of different techniques, like those PSO-ANNs, particle swarm optimization, artificial neural networks.
PSO-ANNs, that sounds like something straight out of science fiction.
Maybe a little bit, but they're already being used in some really cool applications. Basically, they combine those optimization capabilities of particle swarm optimization with those learning abilities of artificial neural networks. It's like having a dream team of engineers working with a supercomputer to design those super stable slopes.
That's a powerful combination, but I imagine it takes a lot of computational power to run those models.
You're right, they can be pretty demanding on the computational front, but the results, they can be absolutely incredible. The research paper highlights a case where a PSO-ANN model achieved an insanely high level of accuracy. We're talking like 99.96% in predicting that factor of safety for a slope.
Wow, 99.96%. That's practically perfect. So PSO-ANNs are like the heavy hitters of ML world.
They are. You need the resources to run them, but when you do, the accuracy is hard to beat.
This is amazing. So many different ML techniques all coming together to tackle this challenge. But I'm curious, how are these actually being applied in the real world? Are they just theoretical concepts, or are they actually making a difference in people's lives?
They are definitely making a difference. There are tons of real-world examples of ML being used for rock slope stability prediction, and they're already improving safety and efficiency.
Like what? Give me some examples.
Well, over in Japan, they're using CNNs to detect rockfalls along highways.
So it's like an early warning system for potential rock falls. It's got to save
It
lives.
does, and it helps with those preventive measures and makes those maintenance schedules a whole lot more effective. And then you've got the mining industry, where they're using RFs to predict the stability of those open pit mines.
I bet that helps minimize those risks associated with mining, which can be pretty dangerous.
Absolutely. And then you've got those PSO-ANNs we were just talking about. They're being used to analyze the stability of those slopes, reinforced with those special rock-socketed piles.
Rock-socketed piles, that sounds intense.
It is. Basically, they're these really long piles that are drilled deep into the bedrock to give that slope extra support. And those PSO-ANNs can analyze how stable those reinforced slopes are going to be, which is, incredibly important for safety.
It's mind-blowing to think that we can use these models to make such precise predictions about these really complex engineering structures. It's like we're entering a whole new era of geotechnical engineering.
ER. But of course, no new technology is without its challenges, right?
Right. There's no such thing as a free lunch. So what are some of the things that are holding back the widespread adoption of ML in this field?
Well, one of the biggest hurdles is data. We need good data, high quality data, and lots of it. MR models are data hungry, and they need that data to be comprehensive and accurate if we want them to perform at their best.
But I imagine getting that kind of data, especially for something as complex and variable as a rock slope, can be really difficult and expensive, right?
It can be. It's definitely a challenge. And then there's the issue of generalization. Let's say you've got a model that's been trained on data from one specific geological setting, like, I don't know, the Swiss Alps.
The Swiss Alps sounds lovely.
It does. But if you take that model and try to apply it to a completely different geological setting, like, say, the Rocky Mountains.
It might not work as well.
Exactly. Every geological setting has its own unique quirks and characteristics, so we need to figure out ways to adapt those ML models to those different environments. And then, of course, there's the issue of computational complexity.
Ah, yes. Those PSO-ANNs and their need for supercomputers.
You got it. Some of these ML models are really computationally demanding, and that can be a barrier, especially for, smaller organizations or projects with limited resources.
So it sounds like there are some pretty big hurdles to overcome. But are there any solutions on the horizon? What are researchers working on to address these challenges?
Oh, there's a lot of exciting work being done. One area focuses on developing more advanced data processing techniques.
So basically trying to improve the quality of the data we have and figuring out how to deal with missing information.
Exactly. And there's also a lot of interest in developing those hybrid models that combine the strengths of different ML techniques.
Like our friends, the PSO-ANNs.
Yes. By combining different approaches, we can create those models that are, more accurate, more efficient, more adaptable, basically the best of all worlds.
That's really cool. And what about the computational complexity issue? Any solutions in sight for that one?
Researchers are exploring ways to develop those more efficient algorithms that don't require quite as much computational horsepower. And there's a lot of interest in leveraging the power of cloud computing to, spread the computational load across those networks of computers.
So instead of needing one supercomputer, we can use the power of the cloud.
Exactly. Cloud computing is getting more and more accessible all the time, so it's becoming a viable option for running even those really complex ML models.
That's awesome. It sounds like there's a lot of hope for the future of ML in this field. But even with all these advancements, we need to remember that ML is a tool.
It is. It's not a magic bullet.
Right. It can help us make better decisions, but we need to use it responsibly and ethically.
Absolutely. And speaking of ethics, I think that's a topic we need to dig into a bit deeper.
Okay, you've piqued my curiosity, but I think we've covered enough ground for one episode.
Agreed.
So stay tuned, because next time on the Deep Dive, we're going to explore the ethical considerations surrounding the use of ML in rock slope stability prediction. It's going to be a fascinating discussion, so you won't want to miss it. You mentioned ethical considerations, and I definitely think it's important to discuss those. But first, I'm still reeling from all the incredible applications you've shared.
It really is amazing stuff.
It's mind-blowing how ML is already making such a difference. But I do want to circle back to something you mentioned earlier, rock-socketed piles and their role in slope stabilization.
Oh, yeah.
It sounds like a pretty complex engineering feat.
It is. Rock-socketed piles are a fascinating solution when you're dealing with slopes that need a little extra support.
Extra support, how?
Imagine drilling these long, slender piles deep into the bedrock, beneath a slope, anchoring it like a giant nail.
So it's like giving the slope a much stronger foundation, reaching down into the solid rock below.
Exactly. It's a common technique used in areas with weak or unstable soil conditions, where the slope itself doesn't have enough inherent strength to resist gravity's pull.
But designing these reinforced slopes must be a nightmare. You've got so many factors to consider: the soil properties, the bedrock characteristics, the pile design itself, and of course all the forces acting on that slope.
It's definitely a multifaceted challenge.
And getting it wrong can have serious consequences.
Absolutely.
That's where ML comes in.
Right.
The paper highlights a study where researchers used a hybrid model, one of those PSO-ANN as we discussed, to predict the factor of safety for slopes reinforced with rock-socketed piles.
Those are the really powerful ones.
Okay, remind me, what was special about the PSO-ANN models again?
They combine the learning abilities of artificial neural networks with the optimization power of particle swarm optimization.
Optimization power.
It's like having a team of brilliant engineers collaborating with a supercomputer to fine-tune the design and ensure the slope's stability.
And what were the results? Did the PSO-ANN live up to the hype?
It did. The model achieved a very high level of accuracy in predicting the factor of safety for these reinforced slopes.
That kind of precision is crucial
It is.
because it allows engineers to optimize the design, minimize the risk of failure, and ultimately ensure the safety of people and infrastructure.
Right. We're always thinking about safety.
That level of accuracy is incredible. It really highlights the potential of these advanced ML models to tackle incredibly complex engineering challenges.
It's a game changer for sure.
As these models continue to improve, we can expect to see even more innovative applications in geotechnical engineering and other fields facing similar challenges.
Absolutely. Like, think about environmental monitoring and prediction.
You keep saying other fields.
Yeah.
What are some areas outside of geotechnical engineering where you see these techniques being applied?
Well, environmental monitoring and prediction is one area where ML is making significant strides.
Interesting. We've been focused on the ground beneath our feet, but what about the air above us or the water around us?
Exactly. For example, ML is being used to predict the spread of wildfires by analyzing weather patterns, vegetation data, and historical fire records.
So instead of just reacting to fires, we can start to anticipate where they might occur and take preventative measures. That could be huge.
It's a game changer in wildfire management.
Wow.
Similarly, ML models are being used to forecast floods, predict drought conditions, and even track the movement of glaciers.
It's amazing how these same techniques that help us understand the stability of rock slopes can also be used to predict and address some of the most pressing environmental challenges we face today.
Yeah, it's really cool stuff.
I'm starting to realize that our deep dive today isn't just about rock slope stability. It's about a much broader shift in how we approach problem solving using data and algorithms to gain a deeper understanding of the world around us.
You hit the nail on the head. This deep dive has really been an exploration of that very shift.
We're seeing a convergence of data, algorithms, and human ingenuity that is changing the face of engineering, environmental science, and countless other fields.
It really is a revolution.
It really does feel like we're on the verge of a new era, where ML plays a central role in how we design, build, and manage our world.
It's an exciting time to be alive.
It is.
But with all this excitement, it's also important to remember that ML is a tool. And like any tool, it can be used for good or for ill.
Okay, I knew we'd get to this eventually.
Yeah, it's important.
Let's talk about those ethical considerations you mentioned earlier.
Okay.
I have to admit, whenever I hear artificial intelligence and ethics in the same sentence, I get a little nervous.
I understand.
What are some of the potential risks or unintended consequences of ML that we need to be mindful of?
It's a valid concern,
It is.
especially as these technologies become increasingly integrated into our lives.
Right.
One of the biggest risks with ML is the potential for bias.
Bias. Can you explain what you mean by that?
So sure,
Okay.
if the data used to train an ML model is biased, the model itself will inherit that bias, leading to unfair or discriminatory outcomes.
So for example, if a model is trained on data that primarily reflects the geological conditions of one specific region, it might not be as accurate when applied to a different region with different geological characteristics.
That's one type of bias, yes.
Okay.
It could lead to inaccurate predictions or even dangerous decisions if the model is applied outside of its intended context.
So context is really important.
It is.
It's not enough to just have a model that works well in one situation. It needs to be adaptable and reliable across different environments.
Yeah.
What other types of bias do we need to be aware of?
Well, another concern is human bias creeping into the data itself.
How so?
For example, if historical data on slope failures is incomplete or has been collected in a way that systematically excludes certain types of slopes or geological formations, that bias will be reflected in the ML model.
So it's like the old saying, garbage in, garbage out. If the data itself is flawed, the model will be flawed too.
Exactly. And that's why data quality and data diversity are so crucial in ML.
Okay.
We need to ensure that the data we're using to train these models is representative, unbiased, and reflects the full range of real-world conditions.
So it's not just about having a lot of data, it's about having the right kind of data.
Precisely. And that requires careful planning, data collection, and pre-processing to mitigate potential biases and ensure that the ML models we develop are fair, reliable, and beneficial for everyone.
Okay, so bias is a major concern.
It is.
What other ethical considerations are there when it comes to ML?
Transparency and accountability are really important too. As these ML models become more complex and sophisticated, it can be difficult to understand how they're making their predictions.
You mean those black boxes you mentioned earlier?
Exactly.
Okay.
If a model predicts a slope failure, we need to be able to understand why it made that prediction.
Right.
This is crucial for building trust in these systems and ensuring that they're being used responsibly.
So it's not enough to just trust the machine blindly. We need to be able to look under the hood and understand how it's making its decisions.
Exactly. And that's an ongoing challenge in the field of ML.
Okay.
Researchers are working on developing methods to make these models more transparent and interpretable, but it's still a work in progress.
It sounds like there are a lot of ethical complexities surrounding ML, and it's something we need to approach with a lot of caution and careful consideration.
Absolutely.
But I don't want to paint too negative a picture.
Right.
ML has the potential to be a powerful force for good, but we need to be mindful of these ethical considerations to ensure that it's used responsibly and for the benefit of all. So it's about finding the right balance between embracing the potential of these technologies while also being aware of the risks.
Exactly. We need to be thoughtful and deliberate in how we develop and deploy these systems, ensuring that they align with our values and contribute to a more just and equitable society.
Okay, we've covered a lot of ground today, from the technical intricacies of ML to the ethical considerations surrounding its application.
It's been quite a journey.
I have to say, I'm feeling a little overwhelmed by all this information, but in a good way.
I know what you mean.
But before we wrap up, I want to revisit those challenges we discussed earlier. Data quality, generalization, computational complexity.
Oh, yeah.
I'm curious to hear your thoughts on how we can address these challenges and unlock the full potential of ML in this field.
Okay, let's do it.
Let's start with data quality.
Okay.
We talked about the importance of having diverse and unbiased data.
Right.
What are some strategies for improving data quality and availability?
One approach is to invest in better data collection methods.
Better how?
Developing more sophisticated sensors and instruments that can gather more precise and reliable data.
So it's about upgrading our tools to get better raw materials for the ML models.
Exactly. Another important aspect is data sharing and collaboration.
Collaborations, how?
By working together and pooling our data resources, we can create larger, more comprehensive data sets that are more representative of real-world conditions.
That makes sense.
It does.
It's like the old saying, two heads are better than one. By collaborating and sharing knowledge, we can create more robust and reliable models.
Yeah,
But what about the data that's already been collected? Is there anything we can do to improve its quality?
absolutely. Data pre-processing is crucial.
Okay.
We can use techniques like data cleaning to identify and correct errors, data imputation to fill in missing values, and data augmentation to increase the size and diversity of existing data sets.
So it's like giving the data a spa treatment before feeding it to the ML models,
I like that.
polishing it up and making sure it's in tip-top shape.
That's a great analogy. These pre-processing steps can significantly improve the quality of the data and ultimately lead to better model performance.
Okay, so better data collection, more collaboration, and some fancy data pre-processing can go a long way towards addressing the data quality challenge.
It can.
What about generalization? How do we ensure that these ML models can be effectively applied to different geological settings?
Transfer learning is a promising approach.
Transfer learning. Tell me more.
Instead of training a model from scratch for each new environment, we can take a model that's been trained on a large, diverse data set and fine-tune it for a specific task or location.
So it's like taking a general purpose ML model and giving it a specialized training course to adapt it to a new environment.
Exactly. It's a much more efficient approach and can help to overcome the limitations of having limited data for specific regions or geological formations.
That's really clever. And finally, what about computational complexity? Are there any solutions in sight for making these powerful ML models less demanding on computing resources?
There are several strategies being explored.
Okay, like what?
One is to develop more efficient algorithms that can achieve similar levels of accuracy with less computational power.
So it's about finding ways to streamline the calculations without sacrificing accuracy.
Exactly.
Yeah.
Another approach is to leverage the power of cloud computing, using networks of computers to distribute the computational load and make it possible to run these complex models more efficiently.
So instead of relying on a single supercomputer, we can harness the power of the cloud.
Precisely. Cloud computing is becoming increasingly accessible and affordable, making it a viable option for running even the most demanding ML models.
These are all really encouraging developments. It sounds like researchers are coming up with some.
It is. And as we continue to learn and innovate, the possibilities are endless.
Okay, I think we've explored the depth of this topic quite thoroughly.
Yeah, we've covered a lot.
I feel like I've gone from knowing next to nothing about ML to having a pretty solid understanding of how it's being used to predict rock slope stability and the challenges and opportunities that lie ahead.
That's been a great conversation. I always enjoy diving into these topics and seeing how much there is to learn and discover.
I'm sure our listeners are feeling equally stimulated and informed.
I hope so.
But before we bid farewell, I'd like to leave them with one final thought to ponder.
Ooh, I like where this is going.
Do tell.
Okay.
Imagine a world where ML models can not only predict rock slope stability with incredible accuracy, but also suggest the optimal solutions for reinforcement and mitigation.
Wow, that's a great thought.
A world where engineers and ML models work hand in hand to design safer and more resilient infrastructure, informed by data and guided by artificial intelligence.
That would be incredible.
Exactly. A world where we can harness the power of ML to create a more sustainable and secure future for everyone.
That's a vision worth striving for.
And I believe it's a vision that's within our reach.
I think so too.
It's a future full of possibilities and challenges, and I'm eager to see how it unfolds.
Me too. And I think the most important thing is to approach these advancements with both enthusiasm and a healthy dose of critical thinking, ensuring that these powerful tools are used for the benefit of all.
Well said.
Thank you.
We need to be mindful of both the benefits and the risks of ML and steer its development in a direction that aligns with our values.
Right.
But for now, I think we've delved deep enough into this fascinating topic.
Indeed, we've covered a lot of ground.
This deep dive has been a real eye-opener, shedding light on how ML is revolutionizing rock slope stability prediction and so much more.
It's been a pleasure exploring this with you.
Likewise.
It's always a delight to engage in these thought-provoking conversations.
I'm sure our listener is feeling equally stimulated and informed.
I hope.
But before we say goodbye, I'd like to leave you, our listener, with one final question to ponder.
Okay, shoot.
Given the rapid advancements we've discussed, how might these technologies reshape the future of geotechnical engineering and infrastructure development as a whole? What new possibilities and challenges will emerge?
That's a great question to leave our listeners with.
It is a big one.
It's a future that we're all shaping together, and I'm excited to see what we create.
Until next time, keep those minds curious and those imaginations ignited.
And may your curiosity always lead you to fascinating discoveries.
It's incredible to think how far we've come in such a short time.
It really is. We've gone from those early days of manual calculations and empirical observations to these sophisticated algorithms that can analyze those massive data sets and make incredibly accurate predictions.
It's a testament to human ingenuity and our relentless pursuit of knowledge. But as we delve deeper into the world of ML, it's crucial to remember that these powerful tools are only as good as the data they're trained on and the intentions of the people who build and use them.
Absolutely. Technology is never neutral. It's shaped by human values and choices. As we navigate this era of rapid technological advancement, we need to engage in those thoughtful conversations about the ethical implications of these advancements.
Thoughtful how?
ensuring that ML is used for the betterment of humanity and the planet, not for short-sighted gains or to exacerbate existing inequalities.
Well said. This deep dive has been an incredible journey through the world of rock slope stability prediction and the transformative power of machine learning. We've explored the intricacies of ML techniques, the real-world applications that are already making a difference, and the challenges and ethical considerations that lie ahead.
It's been a pleasure sharing this journey with you and our listener.
Yeah. And I hope our listener is feeling inspired to learn more about this fascinating field and the countless possibilities it holds. I think it's safe to say that the future of this field is bright, and ML will play a key role in shaping that future.
Definitely. As these advancements continue, we can look forward to even more innovative applications leading to safer, more resilient, and more sustainable infrastructure.
Before we sign off, I want to leave our listener with a final thought. Imagine a world where ML models can not only predict rock slope stability with incredible accuracy, but can actually design the optimal solutions for reinforcement and mitigation.
It's a tantalizing thought. Picture engineers working in tandem with those intelligent systems, seamlessly integrating data-driven insights with their own expertise.
A world where we can build structures that are not only safe and functional, but also harmonious with the natural environment.
That's a future worth striving for.
Yeah.
And I believe it's a future that's within our grasp.
This deep dive has been a real eye-opener for me, and I hope it's been the same for you, our listener. It's clear that ML is a powerful force for change, and it's up to all of us to ensure that this change is positive and beneficial for everyone. Until next time, keep exploring, keep questioning, and keep learning.
And may your curiosity always lead you to fascinating discoveries.